Yesterday we talked about the topic of inertia. We wind up with the inertia part. So today we are going to move forward with the inertia thing. But before we move on to the topic of inertia, I think it is important for us to understand the two important types of the force. Okay? Yeah. Balanced force. Now, if you look at the word itself, balance means normally neither you are going on that side nor you are moving on this side. So you are in a center point, that is balanced force. Now, it is important for all of you to understand that normally in your textbook they have given you an example here. Okay, there is a table. There are two persons, they are pushing this particular table. Okay, and this two person is applying a force of, he is applying a force of 10 Newton in this direction, and this person, he is applying a force of 10 Newton in the opposite direction. Now, as you can see that both the person are applying a same magnitude of force, that is 10 Newton and 10 Newton over here. This table, it is not going to move because they are applying the same magnitude of force. This table will be at rest because both are equal amount of magnitude of force is coming from both sides. So you can somehow cancel it because both are traveling in opposite direction there. Applying in opposite direction. So which is why in that case the net force is equal to 0. Understand? Why? Because 10 minus 10 is 0 in this case. So balanced force, this kind of force where equal magnitude of force is applied from both directions is what we use to refer as balanced force. And as I said, in that case the object is going to be at rest here. Object is going to be at rest. But it is important for you to understand that it is not always necessary for the balanced force to be at rest. For example, we normally identify for two things: object at rest, and second one is object in motion. Fine. Now this is the example of object at rest, because when two equal magnitude of force is applied from both sides, this object, that is the table, that is not going to move. Why? Because the net force is 0. Why net force is 0? Because 10 Newton minus 10 Newton is 0. And this object will stay at rest. But I say it once again that this balanced force can somehow be classified into two parts here. That is object at rest. And in the object at rest example is this one over here. Now this object in motion over here. In this object in motion, what we need to understand is that, let's suppose imagine there is a ball here. Okay, I'm sorry. This ball is experiencing two different kind of force over here. Understand? So let's say now this ball is moving at like 2 meters per second. At 2 meters per second. This ball is moving at 2 meters per second. Now this ball is experiencing two different kind of force. The force number one is gravitational force. That is gravitational force. Gravitational force. And the second one is normal force, which is acting in opposite direction. This normal force is being given up by the soil itself, the ground itself, right? Okay, so this normal force here, normal force, this is in upward direction. Is that clear? Okay. Now, if you look at this ball over here, this ball is experiencing two different kind of force. One is gravitational force, which is downward, and one is normal force. This force, normal force, is being given up by the ground itself. And since this normal force and gravitational force, they are equal in magnitude, they cancel out somehow because they become 0. Now over here, this net force is equal to 0. Is equal to 0. Now I ask every one of you to assume that this ball is moving with little amount of velocity, that is 2 meters per second. Understand? Now, normally in our Earth, we have some kind of different kind of forces which act in the opposite direction. We call this kind of force as frictional force. Now let us assume that in this case here, there is no frictional force, no friction. And secondly, no air resistance. In these two conditions over here, this particular ball, it will move on forever. Understand? And in that case, there is again a balanced force over here. And the balanced force, this 2 meters per second will be over here and will be over there and will be at some different place, because this is a balanced force. Is that clear? Now, secondly, when we are going to talk about unbalanced force. Unbalanced force. Now, in the case of unbalanced force, it is quite different from the balanced force here. Now, this is a table here again, and there is a person, he is applying a force of, let's say, 50 Newton in this direction, and there is another person here, he is applying a force, okay, so he is applying a force of 10 Newton here. Okay, so now by looking at this particular diagram, okay, you will be able to understand, okay, in which direction the table will move. And I'm sure every one of you are going to say the table is going to move in that direction here. One, because the net force, that is how much force is applying, that is 50 Newton. Net force is equal to 50 Newton minus how much force is applying, 10 Newton. So in that case, 50 minus is 40 Newton in this direction. Such kind of force where there is unequal magnitude of force. That means, is that equal 50 and 10? No. 50 Newton and 10 Newtons are totally unequal by nature, and they both are coming from the different direction here, and this kind of unequal magnitude of force applying from different direction, and where the net force is not equal to 0 is what we refer to as unbalanced force. Is that clear? Okay, so this unbalanced force, we are going to deal with this unbalanced force. Okay, yeah. Okay, fine. So here, now last time we talked about an external thing, that is external activity, which allows all the object to move, and this external activity is what we refer to as force. Understand? Okay? Now, we came to another point that is called inertia here yesterday. Inertia. I said before that every object, right, whether it's a small one or a big one or whatever it may be, they have some ability or they have some tendency, or else you can say they have some potential to stay at rest or to stay in motion. Understand? Okay, so this ability or the tendency is what we refer to as inertia. I can give you some example here. Now this inertia, normally I used to classify in the form of 3 types here. That is inertia at rest, and inertia in the case of direction over here, and the third one, inertia in the case of motion. Okay. Now in the case of inertia at rest here, this one over here, inertia at rest. Let me just give you one example, okay. For example, when you are in a bus, suppose a stationary bus, this bus is not moving. So you, what you're going to do, you're going to board the bus, and you are not aware that the bus driver is going to start the engine and he's going to move all of a sudden, right? So in that case, what is going to happen is that the bus is at rest, and you are sitting in a bus, and your body is also at rest. But all of a sudden, what happens when the bus driver begins to move the bus? What happens is that your body begins to fall backward. What is the reason behind that? Begin to fall backward. Why? Because your legs and is at rest, and your leg wanted to stay at rest, but your upper body parts, they move, which is why, since the bus started to move all of a sudden, that is an external force, right? This external force allows our body to move backward. Understand? So this kind of like example is what we used to refer to as inertia at rest. I can also give you another example of a glass here. And there is a cardboard here. On this cardboard, there is a coin here. So you can do this experiment back at your home. It's quite easy here. What you're going to do, you're going to hit this play card over here. When you hit this coin is straight away going to fall down here. Why? Because this particular coin has some ability or some tendency to stay at rest. Otherwise, it should be something like this. When you hit this coin should be going along with this card here. But this is not going to happen. Why? Because this card has his own ability or has his own tendency to stay at rest. And this is what we call as inertia at rest. I gave you two examples here. Now, secondly, in the case of motion here, when we were traveling in a moving bus and the bus driver all of a sudden applies a brake, that is the external force, when he applies a brake, what happens? Our body begins to fall forward. Why our body begins to fall forward? Because our body, actually, they are in motion, and our body is an object, right? Is an object which is in motion. But the bus driver applied a brake and he stopped all of a sudden, but our body has a tendency or ability or potential to move, which is why we are moving upward like this. Do you understand? So this is an example in the case of a motion, that is in the case of, let me write here. Okay, this is a motion here, and this particular man here, he falls forward. Understand? In this case here. Now in the case of direction over here, again, for example, when a bus driver, okay, serves to the right side, our body also begin to fall in this direction over here. When he moves to that side, we begin to fall in that, right? So the point is, what I'm trying to say, that our body also have an ability to stay in whatever direction, okay, trying to oppose that direction, is what we used to call as inertia at direction, right? Okay, so this is in the case of inertia here. Now talking about Newton's first law. Newton's first law. Newton's first law. This Newton's first law is also referred to as law of inertia, because it is somehow having the same kind of meaning over here, law of inertia, right? According to this Newton's first law, what he said was, when an object is at rest, it is going to stay at rest. Understand? What it says, when an object is at rest, it is going to stay at rest, right? Okay. Is at rest, it is going to stay at rest. This is the point here. When an object is at rest, it is going to stay at rest until and unless, here, that is the second point here, that is until and unless some external force is applied on that. Some external force is applied on it. Okay? Is that clear? So did you understand this point here? Newton's first law. Newton's first law, when you are talking about this particular point over here, this is also, I talked in terms of inertia over here, because this law of Newton's first law and inertia is almost having the same kind of meaning. That is why we are going to call this as Newton's first law as law of inertia. Understand? So for example, I say, I take this example of here. There is a glass here, and this glass is having a cardboard over on top here, a playing card, and on this there is a coin here. Now if we are not going to touch this coin is going to stay at rest until and unless if we flick it up, this coin is going to move down here. Understand? So this somehow has the same kind of like motion, just like we talk in terms of inertia over here. That is why we call Newton's first law as the law of inertia. Understand? So let's go for the next one. Okay, now let us understand Newton's second law of motion. Now in the first law, what we said, when an object is at rest, it is going to stay at rest until and unless some external force is applied on that. That means this external force is not actually necessary, but if you apply that, the rest state of the object is going to change. Now, if that external force is applied in real, then what will happen now? In that case, it is important for us to study Newton's second law of motion. Now, in Newton's second law of motion, what it says was that if you apply an unbalanced force, understand, for example, I apply an unbalanced force. When I apply an unbalanced force, what will happen? There will be some sort of acceleration. Because the velocity is going to change. For example, this particular chalk, if I'm going to throw this chalk, what will happen? The velocity will change from 0 to some other velocity. That means in time also. That means acceleration is going to happen. Understand? For example, okay, I have this chalk box over here. But in case if I'm going to apply an unbalanced force, what will happen? This chalk box will change its velocity from 0 to another velocity in a time interval, which we used to call as acceleration. Acceleration will happen, right? So now it is important for us to understand, okay, acceleration depends on two factors. Understand? It depends on two factors. Factor number one, that is net force. How? Let us imagine, okay, this point here. What is this? This is a swinging ball, okay? Small kids, they used to play this. Now let us imagine, okay, if I apply, let's say a little amount of force, what will happen? This will move up and down here, right? It will go in that manner here, swing. But if I apply more force, what will happen? The acceleration will be more. But if I apply less force, lesser acceleration. For example, I have a chalk in my hand. If I throw a chalk on your hat, like in that way, you won't experience that much amount of pain. Why? Because I'm not using that amount of force. But if my net force is something like in a very strong way, in a very high way, what will happen? You will have more amount of pain. That is, it is coming with a more acceleration. Understand? Similar way, let's say when people slaps on your face, right? In a very slow manner, what happened? A little amount of force, what happened? Not that amount of acceleration. But if a high amount of force, then you experience a more amount of acceleration over here. So through this, what we can conclude over here is that force, more force, more acceleration. More force, more acceleration, and less force, less acceleration. Is that clear? That means force is directly, right, straight away, directly proportional to acceleration, which is we are going to keep the equation number 1. Understand? Now, secondly, we talk about the next one, that is mass. Understand? So in the case of mass, let us imagine, okay, this is an object over here, big one, okay, it's having like 50 kg. Now there is another one here, small one, that is like 1 kg. Okay, if I wanted to push that, in which case I will be able to produce more amount of acceleration, because in that case 1 kg is so small, the mass is so small that this particular object can move at more acceleration. But in this case, I can move a very little amount of acceleration over here. So in that case, more mass, less acceleration here. So which I'm going to write here, more mass is equal to less acceleration. I'm sorry, I'll write here, less acceleration. less mass, more acceleration. That means less mass is equal to more acceleration. Is that clear? Okay, so now let us proceed. So in that case, what we can conclude over here is that force is inversely proportional to 1 upon m, and this is, we are going to keep that equation number 2. Is that clear? Do you understand this? Okay, so now this is equation number 1 and this is equation number 2. We are going to sum up both the equation here, right? Summing up both the equation. Right? Okay, so what we are going to get, sorry, this is not F, sorry, this is acceleration. I'm sorry, I was confused what I was writing. Okay, so this acceleration is directly proportional to F and acceleration is inversely proportional to 1 upon m. Is that clear? So now I'm going to write on the opposite side there. Okay, so here, this is equation number 1 here, and this is equation number 2. We are going to sum up both the equation. What we will get, A is equal to F upon m. I changed this proportional here. Whenever we change this, there is another kind of constant coming up, that is K. But for the time being, okay, we will try to understand the important part here. Now this, I'm going to multiply this over here. That means m into A is equal to F, which we can also write as F is equal to mass into acceleration. This is the formula of Newton's second law of motion. Understand? Did you understand this part? I can give you another example here, that is Newton's second law of motion. Okay, this example you have in your textbook. We will try to have a look on this. Okay, so there is a person here. He is catching a ball. Okay, a ball is coming down from there. Now he is going to catch the ball, this ball. Okay, and what he used to do normally, okay, I guess you might have seen the case of like a cricket player, how they used to catch the ball from up there and they used to move down. Understand? So it somehow used to go in that manner here. At last the ball is over here. In that motion they used to move down. Okay? So now let us imagine, okay, the mass of this ball here, mass is equal to like 2 kilogram. Okay, let's imagine. And the initial velocity, that means this ball is coming, initial velocity is like let's say 5 meters per second. Now what is the final velocity? Final velocity, the ball is going to stop. That means V is 0. Understand? Okay? So now in this case, from here, this point to that point, there is another factor of time in that, involvement of time in that. Let's try to keep this time as, let's say, how much we are going to give? 2 seconds. We are going to give that 2 seconds. Now let us try to find out, okay? Yeah, so let us try to find out. Force is equal to, right, mv minus mu divided by t, and mass we are going to keep this as constant. How much is v? 0. How much is u? 5. How much is time? 2. And I'm sorry, how much is mass here? Mass is 2. Now this 2 and 2 we can cancel. And how much we are getting? We are getting minus 5 Newton. Why we are getting minus? Because we are what do you call, reducing the acceleration of this particular object here. Minus 5 Newton here. But there is another guy here, and he is catching the ball now. And what he did, he catch the ball without moving his hand down. Understand? Now, this guy, again, the mass is like 2 kilogram, and initial velocity is like 5, understand, 5 meter per second, and final velocity is again 0 meter per second. Time. Now in this case, this ball is not coming to this portion over here. This ball is over here. Now let's try to say time. Maybe we can give a small amount of time, that is 0.1 second. Understand? So now let's see here. Okay, this ball is not going to come down. In that case, the force is equal to mv minus mu divided by t. And mass, we are going to keep that as common, v minus u upon t. How much is mass? 2. V 0 minus 5 divided by time is 2. I'm sorry, time is not 2, 0.1. Okay? So now when you multiply, you will get something like this here is equal to minus 10 divided by 0.1. This you try to cancel it, you will get minus 100 Newton. So now, if you look at this value here, that is force 5 Newton and 100 Newton, in which case the force is more. The force is more in that case here. That means this much of force can cause you harm to your hand, to your legs also, right? When you are playing a soccer, when the ball is coming from that opposite direction there, you are not going to keep the legs like this here. You are not going to show your legs like this. You are going to show your leg, and it is going to move in a backward direction, along the direction of the motion of the object. Understand? Why we do that? Because we are trying to reduce the momentum of the object. Understand? So, over here, by looking at this one, we are naturally going to take this method as the correct one. And this is the wrong method, because there is a huge force over here, minus 100 Newton. This minus 100 Newton can cause so much of harm to your hand, also can cause fracture on your hand when you are catching a ball from high direction and all. So, Newton's second law of motion, it says that the rate of change of momentum, this ball to that ball, change of momentum, is directly proportional to unbalanced force. The unbalanced force which we are applying in the direction of motion of the object is what we used to call as Newton's second law of motion. Do you understand this? In your textbook, they have given you a clear statement of that. The rate of change of momentum of an object is directly proportional to unbalanced force applied in the direction of the motion of the object. Direction of motion means in that, because this particular object is moving in this direction over here, and your hand is also in this direction over here. Understand? This is about the Newton's second law of motion, because generally when we were talking about Newton's second law, we talk about acceleration, and this acceleration is somehow related with two things here, that is net force and mass. Understand? More mass, lesser acceleration, or more velocity, more force, more acceleration, which is why we got the formula F is equal to m into a. Is that clear? So this is just about Newton's second law of motion, and I have already finished doing the Newton's first law of motion. I hope, hopefully, every one of you have understood quite properly. So I shall see you in the next classes. Thank you very much, everyone.